Hello wonderful person, this is Anton, and today we're going to be talking about the future of our sun, and specifically what the scientists have recently discovered using some of the data from the Gaia telescope, the telescope responsible for collecting very accurate data of all of the nearby objects and nearby stars. And this telescope allowed the scientists from the recent study to collect all of the data on stars very similar to our sun, specifically what we usually refer to as G-type stars. But more importantly, by using all of this data from thousands and thousands of different G-type stars, they were able to then come up with a relative timeline for what's very likely going to happen to our sun and when our sun is going to change just enough to essentially cause the extinction on the planet. So let's discuss this in more detail, but let's also discuss some of the basic ideas in regards to star evolution. Starting with this image that essentially shows us what most of the stars similar to our sun usually go through. So unlike smaller stars, which are M-type or red dwarfs, which basically just turn into white dwarfs directly, or larger stars, such as Betelgeuse, that are going to explode and produce either a black hole or a neutron star, our sun is going to become a red giant. It's then going to throw off a huge layer of mass, creating what's known as a planetary nebula, very likely resembling something like this, and eventually it's going to leave nothing but a white dwarf behind. It's unclear what's going to happen to the planets, but chances are the closest planets, including planet Earth, are very likely going to become absorbed by the star in its red giant stage. And so this is very likely going to be the end of the planet. It's not 100% certain, but it's very likely. Although when it comes to the extinction of all life on the planet, it's actually going to occur much sooner, even before the sun becomes a red giant. As a matter of fact, it's very likely going to happen billions of years before. And that's mostly because of the way our sun and very similar stars evolve over time. It actually increases in luminosity and produces more brightness as it ages. And so every billion years, the total luminosity increases by approximately 10%. Which means that in approximately a billion years, our planet is going to be receiving 10% more starlight. And though it might not sound like a lot, it actually is, mostly because of the way that the heat is retained or released by various planets. And the increase in solar radiation is also going to change the way that weathering happens on the planet, is also going to change how various minerals form on the surface. For example, it's definitely going to affect the carbonate-silicate cycle, which will, with time, dramatically decrease the levels of carbon dioxide. In other words, because of this extreme heat and higher illumination, it's going to decrease CO2 levels. Kind of ironic and I guess somewhat counterintuitive, but that's what the scientists believe today based on the current observations. And so there's actually a really high chance that in about 600 million years from today, the level of CO2 is going to be so low that no plants and no photosynthetic life is going to be able to fixate any more carbon by using photosynthesis. And so, at least for now, it's believed that this is going to be the end of photosynthetic life on the planet. Although chances are life might adapt and use something else. And in about 1 billion years, when the luminosity is about 10% higher, the atmosphere very likely will cause a kind of a runaway evaporation of the oceans. In other words, because of a type of a runaway greenhouse gas effect, even marine life might become endangered because the oceans will slowly start to evaporate. Very likely ending the carbon cycle on the planet, but also possibly ending plate tectonics or any kind of continental activity. In other words, Earth has a very high chance to slowly turn into something similar to modern Venus. Extremely hot, very inhospitable, lacking any kind of carbon cycle on the surface, and with a lot of materials from within accumulating in the atmosphere, creating inhospitable conditions. And that's even before the loss of the magnetosphere. Within about 2 to 3 billion years, the magnetosphere will also disappear and most likely cause a dramatic change in the atmosphere as a lot of lighter elements are stripped away from the planet, making it look more and more like Venus. Although possibly an even more extreme example of Venus, mostly because our planet has way more carbon within it. And so by about 4 billion years from now, it's very likely that Earth will actually become a superheated Venus with temperatures potentially reaching 1000 degrees on the surface. So this right here would be a pretty good representation of the future Earth. Naturally, by then, no modern life would be able to survive, even if it was just bacteria or viruses. And if there's any life surviving here, it would be life we've never seen before. And so within about 4 billion years, it's very likely Earth will become completely barren. But what about the Sun? What's going to happen to our Sun assuming that life finds some other place in the solar system to survive on. So when it comes to understanding how stars evolve, the most important graph in existence is this graph known as the Hertzsprung-Russell diagram, HR diagram for short. In a nutshell, it shows us how various types of main sequence stars, basically stars that are still burning hydrogen, evolve and progress through their lifetimes. And this diagram was created by looking at various stars in existence out there, trying to figure out their age and what's happening on their surface, and essentially putting them on a graph in order to create some kind of a relationship between the age, the mass of the star, and how it's going to evolve over time. Here's one example of this diagram created from all of the data from Gaia's telescope that actually combines millions of different stars. And because the star's mass does not change very much as it ages until later on, but the temperature on the surface changes, as a matter of fact quite significantly, most of the observations from these stars are going to involve temperature and brightness. And so that's kind of what this diagram shows. It shows us the total brightness and the total temperature of the star. And so if we were to plot luminosity and temperature on this graph, here's actually what the shape looks like for a typical G-type star similar to our Sun. They all start with low luminosity and low temperature. It sort of increases up until this point, with this being the peak in temperature, with the current Sun being right here at 4.5 or 4.57 billion years old. And so by collecting the data from a lot of other similar stars, and by actually seeing where they are in terms of luminosity and temperature, the scientists using Gaia telescope were actually able to very accurately predict the rest of the lifetime for our own Sun as well. So as you can see, we haven't really reached our peak in luminosity and in temperature, with the current temperature on the surface being about 5700 Kelvin. But the new data involves approximately 6000 other G-type stars, which you can see right here, and all of them with different masses and in different parts of their evolution. And so let's see what happens to our Sun as it progresses as well. So about right here, 7 to 8 billion years after the formation, the Sun is basically going to peak in its temperature. By this time, Earth, as I mentioned, is most likely going to become already inhospitable and very likely extremely hot. This is about 4 billion years in the future. But following this, the star itself is going to start increasing in size, and because of this, its total luminosity is going to start increasing as well. But its temperature is going to start dropping and is going to become a red giant. So by about 10 to 11 billion years of age, which is roughly around 6 to 7 billion years from now, it's going to become a red giant, and at this point it's most likely going to start swallowing planets like Mercury, planets like Venus, and very likely Earth as well. And right after this, it's very likely going to become a planetary nebula, leaving behind a white dwarf. And that's essentially going to be the end of the solar system as we know it. And by itself, this is a really interesting analysis and a really interesting study. Mostly because Gaia's mission was always to try to map the Milky Way and the stars around it. But by using the data from Gaia, the scientists were able to discover just the G-type stars, similar to our Sun, and then create the most accurate HR diagram that we have right now. And so naturally it means that they found some red giant stars pretty much at the end of their lifetime, but also some really young G-type stars which have only begun forming their star systems. But because Gaia provides them with some of the most accurate data available to us, it means that the current calculations and predictions for the most part seem to be kind of correct. So 11.8 to 12 billion years before the Sun becomes a nebula and turns into some kind of a white dwarf. And all of this of course based on the ideas that were originally proposed over 100 years ago. The ideas from the two astronomers that devise this particular diagram, the Danish astronomer Einar Hertzsprung and the American Henry Russell. Although intriguingly, they did not actually propose them together. They worked separately, and all of this was created 2 years apart. But because of their initial ideas, we now have a pretty clear understanding of what's going to happen to the Sun and what it was like before as well. Which is essentially how the scientists are able to usually predict what's going to happen to various planets with time, but also obviously predicting what the planets were like previously. And here we of course have this one mystery that's still unresolved. The mystery of the Sun when it was much colder, specifically when it was under 1 billion years old. Today this is known as the faint young sun paradox, mostly because it's sort of believed that the Earth should not have been warm enough to produce liquid water back in the days. And we've discussed this in some of the previous videos you can find right there or in the description below. But once we discover more from the Gaia telescope or find something else about the evolution of our Sun, I'll make sure to follow this up with another video. Until then, thank you for watching, subscribe, maybe share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, and support this channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.